Oops, welcome to Module 5, Lesson 11, conducting a simulation to estimate the probability of an event. Sounds familiar, huh? Yes, well, it is more or less a continuation of what we did prior in Lesson 10. A few more twists here and there, a few more questions to ask you, a lot more of you planning what you want to do. Okay, so let's get right into it. Alrighty, so here we go. We have in the last lesson, okay, we use coins, number cubes, and cards to carry out these things called simulations. Okay, another option is putting identical pieces of paper or colored discs into a container, mixing them thoroughly, and then choosing one. Okay, so pieces of paper, colored discs. So, for example, if a basketball player typically makes 5 out of 8 foul shots, okay, 5 out of 8 foul shots, then a colored disc could be used to simulate a foul shot, okay, a colored disc to simulate a foul shot. A green disc could represent a made shot, and a red disc could represent a miss, okay, and the reason we only need 2 colored discs because there are only 2 outcomes, okay. It could either make or miss. Okay, and we need 2 outcomes, we need 2 colors. And in this case, they want to have a green or a red. Okay, green or red. So you could put 5 green discs and 3 red discs. So why would you do that? Why would you do 5 green and 3 red into a container? Think about that for a second. Yeah, exactly. It goes along with this right here because this person is making 5 out of every 8 foul shots generally, okay, so on average, typically, okay, typical. Never a guarantee. Always remember that. All right, so you have 5 green and 3 red. Therefore, this is 5 out of 8 because you have 5 out of the total, which is 8, okay? 5 times he's going to make it, 3 times he's going to miss it, typically, okay? So if you go ahead and put those in, you mix them up, and then you choose one to represent a foul shot. If the color is green, then the shot is made. If the color is red, then the shot is mixed, okay? Of course, this is just a simulation here, all right? So this procedure simulates one foul shot, okay? One foul shot, all right? Okay, so here we go. We have number 1, number 2 here. I'm going to lay it out for you. Just read this to you, and I want you to go ahead and figure out what you need to do. So using colored discs, let's just imagine we have colored discs, okay? Describe how one at-bat could be simulated for a baseball player, okay? An at-bat, that's when that baseball player gets up, okay, to the plate and going to do something. Okay. Now, describe how one at bat could be simulated for a baseball player who has a batting average of, we say, 300. Now, it's really interesting in baseball, and I don't know why they did this, but they did. They made it a little bit difficult to understand why they would say 300. But anyway, if you notice this 300, all you need to look at it is actually 0.3. Okay, so 0.3, which we know to be 30%. Okay, that's 3/10, which also equals 30%. All right. Okay, in baseball, for example, you could be hitting 350. Okay, and that is going to be 35%. So that means, for every 100 times this batter gets up, he gets a hit 35 times. This person over here, every 100 times he or she gets up, they get 30 hits. Okay, all right. So yeah, I hope that didn't confuse you, but that's how them batting 1,000. They say. Of course, you can imagine batting 1,000 and getting a hit every time you get up, which is virtually impossible. So, and they go on to explain it here. Note that the batting average of the 300 means player gets a hit on average 3 out of every 10 times Okay, again, yeah, you could look at that as 3/10 as well. Okay, yeah, 3 out of every 10 times. So what we want you to do, I want you to state clearly what the color represents. So go ahead and use colored discs. What would you, how would it work? And again, just use this up here as a model, okay? How would you describe how you would use colored discs to describe a one at bat for a baseball player who gets a hit 3 out of every 10 times? Okay, so welcome back, and let's go ahead and take. I'd love to take a look at what you've done, but I can't see. Where are you? No. But let's go ahead and see what I wrote here. I wrote, well, a good way to do it, a pretty logical way, easy way. Just go ahead and put 10 discs in a bag. Make 3 of those green, which will represent hits. Okay, and then 7 red, which will represent outs. Okay, a non-hit. All right, so that would be easy. So you're going to go ahead, shake them up, and you can see that your chances of getting a green one would be 3 out of the 10. Okay, or right here, 3/10, which is the same as the batting average of what we say 300. That's a batting average there. Okay, alrighty. Let's go ahead and look at the next one. Number 2. So now another scenario here using colored discs again. Okay, describe how one at bat could be simulated for a player who has a batting average of 273. Ooh, that's a little different, huh? 273. All right, and again, note just like above, a batting average of 273 means that on average the player gets about 273 hits every 1,000 at bats. Okay, so for every 1,000 times he or she gets to bat, they get 273 hits. Okay, so how would you go ahead and use colored tiles to create this simulation in a bag? Go ahead and do that and come on back. Okay, so let's check in on this one. Yeah, it's pretty simple. Actually straightforward. Put 1,000 discs in a bag with an exclamation point after it. 273 green for hits, representing hits, and 727 red, representing non-hits. And again, these colors are arbitrary. Yeah, I'm just picking green and red just because it's in my teacher's notes, and also because green is like for good, go, and red is for stop. So I want to clarify something about non-hits. The truth is, if a batter walks, and they get 4 balls and they walk, it's not considered an at-bat. So the truth is, this really should be outs. And again, I borrowed that non-hits from the bag, from the teacher notes here. Okay. If any baseball players out there want to correct me, please do, because I am pretty sure about that. Anyway, yeah, real simple. That's what it is. Not simple to find 1,000 discs, though. Okay, so here we go. Example 3. Example 3 here is using random number tables. Okay, random number tables. This is very interesting. There are computer programs. I'm not sure what they're talking about here, but there are computer programs that are random number generators. Okay, and they actually for people, for investigators, or like kind of people who are trying to pick a population of people to survey or to do a test on or to ask questions of. They are random number generators that you just you assign a bunch of numbers, and then this computer program randomly assigns numbers. So maybe that's what they're talking about here. I think that's real interesting, and that's in the study of statistics. They use those devices. So yeah, random number tables. So why is using colored discs not practical? There we go. Okay, here we go. For the situation described in example 2, well, we know why. There are so darn many. Where are you going to find 1,000 discs? I mean, I'm sure you could, but that's quite a hassle, I got to tell you. Another way to carry out a simulation is to use a random number table or a random number generator. Okay? In a random number table, the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 occur equally often in the long run. Pages and pages and pages and no, pages and pages of random numbers can be found online. Okay. For example, here are 3 lines of random numbers. I'm giving you right here 3 lines of random numbers. The space after every 5 digits is only for ease of reading. Okay, only for ease of reading. That's space. Okay, so this space is right here. Okay, they're only for ease of reading. You don't just go crazy by looking at all these things right in a row. But they are. This is meant to be random numbers, so it's 2, 5, 2, 5, 6, 6, 5, 2, 0, 5. It reads like that. Okay, it doesn't read like 25,256, 65,225. It doesn't. That's not how it works. Okay, these are read singularly. Okay, like that. All right. So go ahead and just ignore those spaces when using the table. All right. So now to use the random number table to simulate an at-bat for the 273 hitter in exercise 2, you could use a 3-digit number to represent one at-bat. Okay? So the 3-digit numbers from 000 to 272 could represent a hit. And then the 3-digit numbers from 273 to 999, could represent a non-hit. Okay? All right, non-hit. And again, this works out because if you remember, there were, this batter is batting 273. This 000, this right here is actually going to count as one possibility. Okay, so 000 to 273. Inside of this range here are 273 possibilities, and inside this here, 273 to 999, there are 727 possibilities. Okay, all right. So using the random numbers above and starting at the beginning of the first line, okay, at the first line. Hold on, I gotta erase some things here. I'm having trouble reading here. Okay. So starting at the beginning of the first line, the first 3-digit number is 252, which is between 000 and 272. So that a simulated at-bat is a hit. Okay. The next 3-digit random number is 566, which is a non-hit. So let me show you how that looks here. So here is 252. Okay, so we are deciding that we're going to use these as 3-digit numbers, and we have to be consistent with that right now. Okay, you can use them as single-digit numbers, 2-digit numbers, how many digits you want, however. So 252 is going to be a hit because it's between 000 and 272. And again, we have arbitrarily decided this. Okay, we could have started out with 000 to 726 were non-hits, and then 727 to 999 were hits. Okay, so it's just it's arbitrary, but in this case, these are hits. These 3-digit numbers are hits, and then these down here are right here. These here are the non-hits or the outs. Okay. So anyway, back to where I was trying to show you here. Yeah, so there is the number 252, and the next is going to be 566, which is here 5, 6, and then this other 6. You see that right there? That's a 566. And again, just ignore those spaces. The next 3-digit number, as you can see, if you maybe you can tell me what is the next 3-digit number. Yes, indeed, it is 520 right there. Now that 520 would also qualify as a non-hit, okay, or an out. All right. Okay. So you continue on the first line of random numbers above. Okay, just go on the first line. what would the hit, non-hit outcomes be for the next 6 at-bats? Okay, and it says be sure to state the random number and whether it simulates a hit or non-hit. So, for example, you're going to do the next 6, okay? But let me just do the first, actually only the first 2 we did, okay? Here. So the first 2, the first one was 2, 5, 2. Then I want you to put like that and then put hit. Then the next one was 5, 6, 6. Let's say out. Okay. And then the next one, and we did do the next one already. So I did 5, 2, 0. That was also an out. Okay, you see that right there. 5, 2, 0. Okay, so you go ahead and do the next 5. Okay, and we'll get a total of 8. Okay, so go ahead and do that and come on back. Okay, let's see how you did here. All right, here's what I came up with. I had 572 was next. That's an out. 597 is an out. 005 is a hit. 621 is an out. And 268 is a hit. So, looks like how many hits do we have? 1, 2, 3 hits and 5 outs. 3 hits and 5 outs. Okay, so yeah, well let's move on. Oopsie, sorry. Let's move on here. Here we go. Baseball player. Okay, example 4. All right, so a batter typically gets to bat 4 times in a ball game. I'm not sure how typical that is, but I would say more or less 3 times. Again, you baseball players out there, correct me if I'm wrong. But anyway, a batter typically, we'll go with what they're saying here. A batter typically gets to bat 4 times in a ball game. Let's go ahead and consider our 273 hitter here from the previous example. Use the following steps. Okay, use the following steps here, and the random numbers shown above. Okay, so those random numbers that we've already used to estimate that player's probability of getting at least 3 hits, 3 or 4 in 4 times at bat. 4 times at bat. Okay, so we are trying to estimate the probability of getting at least 3 hits in 4 times at bat. Okay, so what I want you to do now, this is kind of a we are planning here. So let's go ahead and have you do just A and B on your own. Just go ahead and pause. Do A and B because they're kind of trying to get you here to think through this problem, and so go ahead and do that, and then come on back, and then hopefully you can go ahead and do your 12 trials. So let's do A and B first. Okay, so let's check how you did here on this planning phase here. Okay, so describing what one trial is for this problem. If you described it, it would be something like this. One trial would be 4 3-digit numbers. Okay, so 4 3-digit numbers circled or identified, okay, in a row would constitute a trial. Okay, because remember, we are trying to find out the probability of getting at least 3 hits, 3 or 4 in 4 times at bat, and that's the key right there. Okay, each trial has to be. You have to do it 4 times. Okay, 4 times. It's like when we did the coin rolls. I mean coin rolls. the die rolls or the coin tosses. Okay, we would do them a certain number of times depending on the context of the problem. In this context, we're looking at 4 times at bat. We're trying to find out how easy or difficult it is to actually get 3 or 4 hits in a given game, you know, for your 4 times at bat, right? Yeah, so in this case, this one here, a first trial with these random numbers, okay, the numbers we have in your binder there would be 252, 566, 520, and 572, okay, and those are taken right from the random number generation list, okay? And B asks you to describe when a trial is called a success and when it is called a failure. Well, a success, okay, a success or a successful trial is getting either 3 or 4 hits. Okay, 3 or 4 hits. A failure is getting either 1, 0, 1, or 2 hits only. And as you can see, this is a failure because we only had 1 hit. Now, it doesn't mean it's bad data. It's just a failure. It did not happen in that one trial. Okay, so you're going to go ahead and simulate 12 trials. Okay, right here, you're going to go ahead and simulate 12 trials. Go ahead and start from right after 572. Okay, on the random number generator. Okay, go ahead and start after that. I think we have four other random 3-digit numbers chosen already. So go ahead and use those 4 for your next trial. Okay, and then go 11 more. So again, you're going to simulate 12 trials, 12 more trials, above and beyond this one right here that we did. Okay. All right. So go ahead and do that, similar to that, and come on back and we'll check in. Whew, that took a while. Man, oh man. Yeah. So here we go. We had to simulate 12 trials. Okay, 12 more trials. So here's what I came up with. I don't know. It's easy to get lost in these numbers, these random numbers, but hopefully we get the same thing. That was my first trial. Well, that's the first trial over here. And then second trial, third trial, fourth trial. Okay, so then I went back and did some more. I was like under the impression I was done, but I had just done 12 more numbers, 12 more 3-digit numbers, not all of them. So I had to go back and continue. 557. You can see a lot of failure. Okay, and again, failure is not bad. I mean, it's not that you succeed or you fail. It's just that your test here, your outcome is either a success or a failure, and that's how we gather data. Okay, and there we go. So, as you can see, this was a pretty bad result for this batter here. Okay, because as we can see, we can go ahead and look at and estimate the probability that our 273 batter or hitter gets 3 or 4 hits in 4 times at bat. Okay, and hopefully you got the same numbers as I did, but we can go ahead and see. So again, a success. Let's go ahead and success. We'll put a yellow streak through it. And then failures, will put a red streak through it. Okay, so we already said that this was a failure because there were 3 outs there, all those in the 500s. Here we came close. We had 2, this one and this one, 2 hits, but that still didn't meet our criteria. Okay, or meet our success threshold, and our success threshold was 3 or 4 hits. Okay, the next trial, again, just 1 failure. Another one, just 1 right there, failure. Actually, there were no hits there. 1 hit there, failure. 1 hit there, failure. No hits, failure. No hits, failure. No hits, failure. Oof, boy, that was getting really depressing. Whoa, we got one. Boy, I tell you, I was really rooting for the small numbers to come up. Yeah, so we got 3 out of 4 there. Okay, 3 out of 4. And yeah, that's it, failure. Okay, so what I calculate here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So out of these 12 trials here, 12 trials, there was only 1 that was a success. Okay, 1 out of 12, and let's go ahead and figure that out. I should know this by now. Hold on one second. And that is 0.083. Okay, so not a great probability. That's an 8% probability that this batter, this hitter, will get 3 or 4 hits. So that's not to say anything for this hitter, him or herself. in terms of their batting average, because their batting average is still going to be 273. They still get, 273 hits every 1,000 times at bat, okay, which wouldn't be the case here. But that's not a batting average. This one we just calculated, okay? That's not a batting average. That is just the probability of this person, this particular hitter, getting 3 or 4 hits at 4 times at bat, okay? Pretty slim chance, okay? You get a batter hitting going 4 for 4. That's low probability. Okay, so we went ahead and did that. We and again, compare your estimate with other groups. We didn't have any other groups necessarily, but you can compare yours to mine. Sure, they're the same if you followed along with the random numbers, 3-digit numbers like I did. Okay. All right, so here we go. Next example here is birth month. Okay, this is interesting. These are always fun things to do. We all love our birthdays, don't we? In a group of more than 12 people, is it likely at least 2 people, maybe more, will have the same birth month? Okay, and why? And then try it with your class. Okay, we're going to work that out here. But if you would, go ahead and just answer that question. Do you think in a group of more than 12 people, it is likely that at least 2 people, maybe more, will have the same birth month? Think about it, and give it a whirl down here. Let me know why you think what you think, okay? And then we'll do something. Well, I hope you didn't have to think too hard about that one, okay? Because there is this group of more than 12 people, okay? More than 12 people. Now, what do we know about months? There are 12 months, okay? There are 12 months. Now, we actually have 14 in our class, and if you include me, that would be 15, okay? Our class that once was, and no longer is. No, it is. It is. Anyway, yeah, 15. Therefore, if the first 12 people had, had different birth months, okay, had different birth months, that 13th person, unless they had different months, because I want to just cut this short, the 13th person would have to share a birth month, okay? And that's probably not the case anyway. That the first 12. I think the odds of there being every single month of the year represented in a class of more than of 15 would be pretty unlikely. Okay, but yeah. So the first 12 people would have to, even if they had different months, the 13th person would have to share a birth month. My birth month, by the way, is in April. If anyone cares to know, anybody else have an April birthday out there? But anyway, let's go ahead and look at this, but let's look at this in terms of the next. Now, the next question is a little bit more interesting, okay? Now, again, the probability in a group of more than 12 people that there will at least be 2 people that share a birth month, that probability would be 1.0, okay, or 100%. I mean, it would, it's clear, okay? It has to be, okay? Now, suppose that same question is asked for a group of only 7 people, okay? Only 7 people. Changed it a little bit here, okay? Are you likely to find some groups of 7 people in which there is a match, but other groups in which all 7 people have different birth months? So now in the following exercise, coming up, following exercise, you will estimate the probability that at least 2 people in a group of 7 were born in the same month. Okay, are you ready for this? All right, here we go. Okay. And again, a little pre-planning, a little planning here. What might be a good way to generate outcomes for this birth month problem? What might be a good way to generate outcomes? And again, this lesson is talking a lot about the planning process, okay? Might you want to use coins? 50-50 chance. Number cubes. How about cards, spinners, colored discs, random numbers? What would you use in this situation if we're wanting to predict or estimate the probability of more than one person sharing a birth month in a group of 7? Okay, so think about that and jot something down and come on back. Okay, let's go ahead and look at this first part, this number 1 here, and kind of see what you said. This would be a great thing to do in classroom. Well, again, we could probably eradicate some of these, okay? I mean, coins are definitely not going to work, okay? There's only two choices, 2 possibilities, okay? 50-50. 2, we're looking at something that can give us 12 possible outcomes, okay? We need something that's going to give us 12 possible outcomes, and a coin is not going to do it. Number cubes won't. I mean, those are our standard number cube will not, because that has 6. 6 sides. Now there are some things called. There are different types of rolling devices, as you've seen before. But there is one called a dodecahedron. I know I spelled this wrong. But anyway, dodecahedron, that is actually a 12-sided die, or 12-sided, we'll call it a die. Okay, a 12-sided die, dodecahedron. That would work. Each one could represent a month each side. It's probably usually 1 to 12 or 0 to 11 or whatever. But yeah, dodecahedron. But beyond that, that's probably not something you would have put down. Some other possibilities are cards, a deck of cards. You could have, because in a deck of cards you have the ace, then you could have ace 1, 2, 3, 4. Those of you who play cards, 5, 6, 7, 8, 9, the 10. So now we're at 11, and then we could use the jack or whatever. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we can say, starting from the ace, well, actually, why don't we do that? Why don't we just, I'm just trying to think this through here. Take the ace out, and then just maybe take jack and queen. All right, so now you have, each of these is good because they're the number months, so that's January through October. And then you could have the jack be November, and then the queen be December. Okay, yeah, so you could use that. You could use cards, okay, and you could use spinners if you had a 12 segment spinner. It had to be fair. Okay, 12 segment spinner. Colored discs. Oh boy, I guess you could. 12 discs could work if we could. We could write the names of the months on them, or we can even put numbers on them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. To represent the month. So we could indeed use colored discs, 12 of those marked. If you had 12 different colors, which you surely don't, and of course random numbers would work. All right, we could always use random numbers. Okay, random number table. All right. Okay, so all right, let's move on here. So how would you go ahead then after this, after deciding what type of device we're going to use here? We let's just say cards. Okay, let's say cards. Do you guys have cards? You guys all probably have decks of cards in the house, right? So I'm thinking, I'd love everybody to do this at home. And again, I can't make you do anything like this, but if you did, it could be a lot of fun. If you got a deck of cards and went ahead and set it up from 1 through the queen, okay, to represent the months. Okay, let's decide on that. Now the next question would be, how would you simulate one trial of 7 birth months? Okay, one trial of 7 birth months. If you would go ahead and decide on how that would work, would you do that, think about it, and then come on back? Okay, so how would you simulate one trial? And I didn't specify this, but I'm just thinking, I was hoping you'd maybe talked about working with the cards, okay, with the playing cards, since they seem to be, I think, the easiest thing for you to get your hands on, unless you have a dodecahedron at home, okay? But yeah, how would you go ahead and simulate that? But I was just thinking, could do it this way. So a list of 7 birth months would constitute a trial. Okay, so we would have to pick 7 times. Really, though, important, very, very important in this case, is that you would need to replace. Okay, you need to replace the cards. Dip your hand, put the cards in the bag, numbers 1, then through the queen. Put those in, shake them up, hand in, pull it out, and then record, put it back in, shake it up. Same thing again. We would need to replace because every member of this class, or group, we're talking about 7 people, okay, so 7 people would need to have the same probability, 1 out of 12, of getting any birth month in there, okay? So yeah, that would be fun, lots of fun. I hope you guys do this at home because it sounds like a real hoot to me. I know, I like this stuff. But before we get on with this simulation, we need to ask a question here. So how is the success determined for your simulation? Okay, how would the success? And again, we have to go back to the question, or what we were talking about, and what we were trying to figure out. We are trying to figure out the probability in a group of 7, the probability of someone, 2 people. Hold on a second, I gotta check this out. I'm sorry, I just kind of lost track. Yeah, we're trying to figure out the probability of there being multiple people born in 1 month. Okay, so out of a group of 7 people, what is the probability of at least 2 of them sharing a birth month? Okay, that's what we're trying to prove. So, what would a success be, therefore? Okay, well, success would be, well, actually, you think about it and come on back. Okay, well, yeah, a successful trial would have a month or months chosen more than once in 7 picks. So, for example, I went ahead and just did this real quickly. What I just used tiles, those plastic uniform tiles I have, yellow ones, and I just wrote the names of the months, or the abbreviation of the months on those, and put them in a bag, shook them up, picked, put it back, shook them up, picked, put it back. So I came up with this. Here was one of my trials. My first trial was December, October, July, December, October, believe it or not, April. Can you believe this? Okay, so with my picking, I actually picked, I had 3 different months, April, October, and December, that were picked multiple times. But that is only going to be considered a success. So it's 1 success. Okay, it's not more than 1. It's not 2 successes or 3 successes because 3 different months were duplicated. That is just 1 success. Okay, so and then here, so how, number 4 asks, how is the simulated estimate determined for probability that at least 2 in a group of 7 people were born in the same month? Okay, how do you determine it? Well, you're going to do, of course, if you choose to. I'm not going to do it, honestly, but if you do it, I would be really, really happy. It'd be fun to actually see what you did. But you would have to do it a number of times. Let's say we do it 10 times. How about 20 times? 20 times. Do it 20 times. So you're going to take the number of trials that you did, which would be 20. So you're going to do this over 20 times. Okay, so this is just 1 time right here. Okay, that's your first. And again, I think you know this because we've been doing this already. I don't mean to treat you like you don't know anything, but I just want to reiterate some things sometimes just to try to make it clear. Okay, so then you would put the number of successes, okay, on top, and you're going to divide that by 20 if you're going to do it 20 trials, and that would give you your whatever, and or your percentage, blah blah. Okay? Yeah, do it if you have the time. If you have nothing else to do, no, I'm kidding, because I know you have lots of other things to do, but if you would do it, I think it might be Might be fun. Do it together. Do it with a friend, or do it with your sister or brother or your mom or dad. Okay? So yeah, so that's how you would determine it. And again, we've been doing this before. Okay? All right, so we're going to close right now, and in our lesson summary here. So in the previous lesson, okay, that was lesson 10, you carried out simulations to estimate a probability. In this lesson, you more or less just had to provide the parts of a simulation design. So you became more or less a designer, okay, of these simulations. All right. You also learned how random numbers could be used to carry out a simulation, and they do exist on the internet, online. Go ahead and all you have to do is just Google random numbers, and it's really interesting. Again, I mean, you know, people in advertising and industry, and they use these random number lists a lot. Okay, so again, to design a simulation, you want to identify the possible outcomes. Okay, for example, with the birth thing, it was boy or girl, remember? Decide how to simulate them, and in that case, it was flipping a coin, okay, etc., etc. You're going to specify what a trial for the simulation will look like, okay, so we want to find out three, what the chances are, what the probability is of having a boy and three births in a row. Your simulation trial is going to be 3 flips of that coin, okay? And you have to decide what a success and a failure would mean. Okay, what would connotate a success and what would be a failure? And make sure you carry out enough trials. Okay, and very often in statistics, 30 or more trials is usually required for any kind of surety, but still doesn't ensure anything really, but you want to ensure the estimated probability gets closer to the actual probability as you do more trials, okay, and that actual probability is more or less the theoretical probability, okay. So there is no need for a specific number of trials at this time. However, you want to make sure you carry enough trials so that the relative frequencies level off, okay? And this idea of leveling off, because if you do 2 or 5 trials, you could be really, really lopsided one or the other. Even when flipping a coin, flip a coin 5 times, you may get 5 heads in a row. Doesn't make sense truly to estimate, therefore, that the probability of flipping a heads is 100%, because that's just not so. But if you did that over 100 times, 500 times, and again, remember we talked about this a few lessons ago about the person who did it 24,000 times, flipped a coin, and it came really, really close to that 50-50 mark. Yeah. Okay, so I hope you enjoy this probability stuff, and one more lesson after this before your mid-module assessment. All right, and have fun.